Okay, good morning, everyone. So today we'll talk about, as I mentioned before, really the foundation of what we wanted to cover. I think we have done, but now we'll just give you basically kind of how we can apply what we learned in different contexts. So today we'll talk about autoencoders. And okay, so we'll look at fully connected autoencoders, convolutional, regularized, or denoising autoencoders. The only autoencoders we'll not cover is the variation autoencoder, very powerful one, but needs quite a bit of math that we don't really have space for it in this course. And then we look at the relationship between PCA and autoencoders, and we look at how you can visualize the latent space, which I think is very important. And then the pooling and unpooling mechanisms. Okay. So let's look at supervised learning. You turn off these slides. So supervised learning, as we already covered this weeks back, you have pairs of data. You have the data, the input, and then you have some labels or annotations for them. And the whole model is how can we really map this input to the output or to the labels that we have. Classification, regression, as just examples, segmentation, and so on. And then we have the unsupervised learning, where we don't really have any labels whatsoever. And now we'd like to understand what are the underlying business structure or features of the data. And so once we know that, then we can use those for some other applications. And clustering was one of the things that we talked about. That is unsupervised learning. Okay. So if you look at the autoencoder, this is kind of the overall structure for it. So what you have on the left-hand side, you have the input data, capital X. And then what you are really, the overall goal is to reconstruct X. So that's why we have X hat in here. So this is X hat is the reconstructed version of X, right? So it's not identical, but it's an estimation, an approximation of what X is. And that's why we call it a reconstruction of that X. In the middle in here, we are really going through a representation space. So if you look in here, going from the X, this representation space, we go through a certain process. And just the easiest way to look at this is just Fourier transform. Right? So basically, you go from X to the Fourier coefficients, you go through the transform, right? And then once you have the coefficients, then you go in the inverse Fourier transform, and then you bring basically X back. Right? So the only difference in there, basically, if you use all the Fourier coefficients, then you can really get X back completely as it is. But if you really start to compress and not use all the coefficients, then maybe X in here is not as identical, or is not identical to X. So that's an approximation. Same way in here, we have an encoder. So we have an encoder structure here that takes the input X and produce a representation space. And then we have a decoder here. And then basically that maps the representation space into the original data X in here. That's an X hat, because in the process, we lose some information. Right. So now, if you look at how we train this, you take an input X, right? And then you really feed forward, because this is, you can imagine this is basically a neural network. Could be fully connected, could be convolutional network. But we really go through a feed forward, right? All the way here, we look at what X hat, and we are really trying to minimize the error between X hat and X, and we get back propagate, right? So we keep doing that. Just as we did in the CNN case, right? Or the MLP. So feed forward, we look at the loss between X hat and X, try to minimize that loss, and we keep doing that iteratively until we reach a certain criteria, right? And once we converge, then we have a model. Now, what we have a representation space in here. We call it a latent space that really represent our data. So now, once you have this space in here, then it's really up to you what to do. You can use the entire model here. You can use this space, the representation space in here, for some other applications. So now, because you, for example, your data is very, very large, but now you want to do a dimensionality reduction, just like a PCA. And now you can use this representation space. And I think one of your teams in here will appreciate this, because they are using a PCA kind of in their project. So it's once you have that, in quite a bit of different things, what you could do with that latent space. Any question about the overall idea behind autoencoder? Are we good? Okay. Yes. So we can really kind of rephrase what our goal is to learn a lower dimensional representation Z for the data X in here. So the data really dimensionality for the input data is dimension capital P, and then what the representation space in here is capital K, where K is smaller than P. So in this case, we're using a lower dimension, but not necessarily. We'll look at the end of the lecture today, where in some cases we like to have a sparse representation of the data. In that case, the dimension of the latent space will be larger than capital P in this case. But we need to impose some regularization, like like sparsity conditions, so we can really have quite a bit number of zeros. But for now, if our aim is to lower the dimensionality of the input, then basically capital K will be smaller than capital P in here. Once we do that, then in general, in AutoEncoder, the latent space Z describe the underlying structure, right? So what you can think of is, again, I'm trying to use signal processing background, like if you have Fourier transform, and you have the DC has a meaning, the first coefficient has a meaning, the second coefficient has a meaning. It's the frequency components, right? Same thing in here. We don't really have that kind of same simple way to describe what these coefficients are, but they really describe the fundamental structure or the features that describe our data X in this case. Okay, so you can think of this. We are literally doing some kind of a compression, although there's some kind of in the image processing class we talk more about how we can really make this system into a compression of images and videos and speech signals. But the overall idea is the same. We can really use it for compression in this case. But also, that's one way to look at it. But also, in many different applications, we can take this space now, right? Once you have the model ready, then you input your data. You take the latent space. Now your data which is unannotated. You take that basically as your representation of the data, and then you use it to train something else, right? You can train a classifier or some other application, right? Because now, imagine that you really don't have enough power to train from scratch for your huge amount of data, because the dimensionality capital P is very large. Then you just run it through this this encoder. You give the space in here, representation Z, and then use Z as an input to another CNN to do classification, for example. And that's basically also is kind of a fine-tuning application of AutoEncoders in this case. Okay. Okay, so if you look at the parallel, we have seen this before. If you take an input, you want to do a lower dimensionality process on it. That's basically kind of the most common algorithm is PCA, right? Principal component analysis, right? Where basically you take that X, and then you really decompose this or transform X into the latent space Z using this basically transform, which is V sub K, where K is less than the dimensionality of the input signal P. That's PCA, right? And the idea in here, basically, we look at the main components that he described our data X in this case. If that's the case, basically, we can reconstruct X from our V and VK using this equation here, as we have seen this in the second homework, I believe, or the first one. So we have X times VK transpose. And basically, once we have that, then we have an error between X and X hat, which is the reconstruction error that we have in here. But this is really is a straightforward case. And also in here, the dimension of K will determine how much of an error we have in the reconstruction side, right? In this case, and we did that in the homework where you can remove some components, then the reconstruction error will be larger and larger in this case. Okay, so if you look at the difference, can we really redo that? Can we use an autoencoder in lieu of a PCA? And the answer is yes, for a specific structure. So this is, if you remember, the PCA is a linear dimensionality reduction algorithm. So it's linear, right? That's basically the whole idea of PCA, right? So now, can we design a linear autoencoder? And the answer is yes. What we will do is we will have a single fully connected layer here, a single fully connected layer here. This fully connected layer is really the VK. This one here is the VK transpose, right? So basically, that's the whole idea. So it's a linear fully connected autoencoder has a fully connected layer and also has a linear activation function. We're not using any nonlinear. We don't use ReLU or any of the sigmoid or any of those things. It has to be a linear activation function. And then once we have that loss function here, then basically that's nothing but the same as the reconstruction error in the PCA case. So that's exactly what how we can use a linear autoencoder to really give you a PCA in here. The only difference in here is basically you have in the PCA you have like you have this orthogonality in here. Yeah, you have this basically projections in here is linear and orthogonal to the space, right? That's what we have as a condition for the PCA in here. If you are really training this autoencoder, not necessarily you will get this perfect basically projection, right? So you'll not really get this perfect projection here because you are training this on the data, right? This is the only difference between this structure as an autoencoder and a PCA in here. But you get a very, very close approximation of what the PCA will give you if you do it that way. But again, this is a linear autoencoder, so you're not really exploring the nonlinearity in the input data in here. Okay. Okay, so now we really can expand that idea and start to look at what we can do to explore nonlinearity in our data, and that's basically where we go to nonlinear autoencoders in here. So let's look at the motivation here. For example, if you look at your data as the MNIST data set and you have just 2 digits, 1 and 0, then what you really want the representation space in here at the same time, it captures basically the features of a 1 as well as the features of a 0, right? And you can see basically the features of a 1 is more of a straight line kind of features. The digit 0 in here is more of a circle or curvatures in here. So these are 2 different features, but you want your Z to encapsulate those 2 features if you really want to encode 1 and 0. That's basically where nonlinearity comes handy. So do the same thing, but now we don't really have just linear activation functions. We have a general encoder. We refer to it as E for the encoder, and theta is our model operating over the X. And then we have a decoder in here, which is the generator, right? Because this is very similar. You can see this same language as in GANs. Basically, this is a generator. Why? It generates the data given a latent space, right? It's very, very small, similar concept in the GANs as well. But we put it in here together as basically kind of almost like an encoder decoder shape. So this generator in here takes an input latent space, and then it really produces our X hat, right? So it really operates on the Z. That's the latent space that we have in here. So we have an encoder, a decoder, or an encoding function, a decoding function in here in our autoencoder. And now, once we have that, then that's where the training comes into the picture. We have our data X. As you can see, we don't really need any labels, right? All what we are really worried about is we would like kind of to reconstruct our X in here. And we'd like to, our whole purpose is to minimize the difference between X and X hat, right? So in this case, for example, if we look at the mean square error as the loss function, then we are really minimizing X minus X hat square, right? So we don't really use any labels in that case. So we could really use something as a fully connected layers, right? This is an MLP. If you just look at the left-hand part, like you have X, you have what you have in here. This is very similar to what an MLP. We have seen MLP at least twice in this course so far. So this is really nothing but an MLP in this case. But what the difference is, in the final, after the final layer in here, we have basically the mapping into the classes, right? That's what usually we have. But now what we do, we really attach to it a generator. Basically, it's really nothing but a G function. That's, you can see, is really reverse the process that took place in the encoder. So you go from the latent space, and you can see basically you're really doing pooling because you have the dimension really increase and so on, all the way until you try to really map back. So the dimension of the output in here is the same as the dimension of the input in here, right? Because you are trying to reconstruct X in here. And in the process in here, because you are using nonlinear activation functions, right? You are using an optimization to minimize the mean square error loss. You will have difference between X hat and X. It will not be identical, X hat to X in this case. And this is really very, very simple, straightforward data in that case. But in general case, the X hat will be different from X in here. So if you take As an example, a grayscale image, digital image of 3 is 28 by 28, one channel, right? 28 by 28 by times 1. So you can really have a dimension here of 784 as 28 times 28. That's basically your input vector in here. And then you do the processing here, and then you reconstruct the same vector dimension here, right? But what you will find out is that the reconstructed digit in here, the image is blurry. It's blurry because it's really because you lost some of those high frequency edges in the process. So there's a difference between basically what you have in here and what you have as an input in this case. So as an example, you can really have your first fully connected layer as dimension 128. You can use a ReLU. The next one is 64. You use the ReLU, and then you have 32. You use the ReLU, and then 64, 128, and then back to the dimension originally. So in this case, you have the input dimension is 784. The latent space dimension is 32, right? So that's basically, this is capital K, which is 32. Capital P is 784, right? Because there's a different, the dimension, that reduction, that compression is really happening in here, right? And that's what, if you do that, then you will get this kind of comparison. What we have in here is the latent space dimension is 32. We have on the left-hand side, we have fully connected autoencoder with linear activations or linear layers. So this is just, we can just say linear autoencoder, fully connected autoencoder. This one is the nonlinear, and we are using a ReLU in this case. So these are the input digits, right? And these are the reconstructed digits. So you can see 1, 2, 3, 4, 5, 6, 7, 8. I mean, all of them really look reasonably well. The only thing is basically you can see they are very blurry, right? In here. So the mean square error is .0.0677. And then if you use a nonlinear fully connected autoencoder, the same input, you get this, the reconstruction. So you can see the reconstruction here is much better than what you have in here. Although the mean square error is not really that of maybe high significance, but you can just visually look at this and say, okay, we have sharper digits in here compared to this one in here, right? And why is that? Because the nonlinearity in the autoencoder, it managed to really learn the features that represent basically the linear part of our digits in here. Question, yeah. Say it again. We're using a ReLU, right? Yeah. Why do we have a sigmoid? We don't have a sigmoid. No, this is very different. Yes. Yeah. Let me repeat this because there's a question about the last layer is sigmoid. So if you look at a classification function, we stop here, right? So usually we have your input, this is the last layer, and then after that you have the sigmoid, and then you input your classes, right? Because you map to the classes. We don't do that in here, right? So this is a new 128 neurons with ReLU, right? Same thing in here, 64 of them, 32 of them, and here we are doing a reconstruction. So everything in here is just basically is again neuron with ReLUs in here, and then just mapping to these ones. And so basically, we are not doing any sigmoid. Right? We are not classifying. Right, we are trying to reconstruct, right? So the best way to look at this, this one is very, very important. So whatever you have between the input and the latent space is an encoder. So you are encoding the data into some kind of a latent space, and then you have a generator where you are decoding the latent space, right, into back reconstructing the data itself. So we don't do any classification in this case. You could build on top of this for classification. You can take the latent space after you finish training, right? And now you have your inference, you have your testing data, you input to the encoder, you stop here, you take the features, and then you input these to another classifier. You could do that, right? Now, I was discussing with a classmate in here last week on Monday. Is that much better than training from scratch for a CNN? And I would say basically it's not necessarily, right? I think trusting the CNN itself to come up with those features and end-to-end is, to me, it's in most cases it will be a better job, right? If you manage to train it very well, but it's worth trying, right? For some deployment applications, it will be the case. So we are not really doing any classification. These are really reconstructed. We are not classifying this digit as one. So we're not doing that. Otherwise, what we will have in here is really class 1, class 2, class 3, right? Well, not necessarily the so the autoencoder reconstructed this 9 into this 9. Similarly, the nonlinear flow-connected autoencoder reconstruct this 9 into this 9, right? This one is sharper than this one, and the reason is because we have the nonlinearity in our ReLU activation functions. Does this answer the question? Yeah. Yes. 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 I mean, we repeat the question basically early on when I talked about in the classification, the first chapter in the course, right? If you don't really use any activation function, you have W times X plus B, then all what you're doing is just linear operation, right? There's no nonlinearity. The magic happens when you have these activation functions, when you have the linearity, right? That's where, yes, it makes optimization more tricky, but that's where the magic happens to really understand the underlying features of the linearity in the input space. Okay. Okay. So this is unsupervised, basically, without requiring any labels. We have some kind of reconstruction errors because we are losing some information of the input data. And then we'll talk about this. Hopefully I will be able to have at least one lecture on anomaly detection because I think that's a very interesting application. Okay. Yes. Oh, there's a lot of applications. So the question is, what are the different use cases, right? So if you really want to have, for example, one of my former students, his work was, if you have a very complex input data, right? And I mean, the easiest for us just to look at an image, but it can be, speech, it can be medical data, it can be finance data. And the idea is, imagine that there's a very famous paper where you input a chair, right? Like you have a dining room, right? So you have the chair, you have a table, you have, window and so on. And now, can we really get to a point where we can manipulate the latent space, where we can remove specifically representations for the chair, but not the table in the same image? Right? So can we really have this kind of decomposition into the latent space where we can start to now manipulate the data, right? And you can think of that basically, that's kind of where the GANs come into the picture. That's where the decoder side come into the picture, right? Can we do that? But all of that depends on how do you do that? How do you do this in the latent space, right? If you take another course, and I think we'll have a new course by a new professor that will start from where we stop, like start with variation autoencoder. Variation autoencoder, basically you constrain your latent space to be Gaussian, right? So this one here becomes a Gaussian, and so and that's basically where the math becomes a little bit, more involved than what we have right now. So once you do that, then that's basically you have quite a bit of power. Now you have a target, right, where you have this Gaussian. I start to look at this as Gaussian. You can just like 2 parameters for each Gaussian, and you start to manipulate basically your latent space. There's tons of different anomaly detection is one of them, right? Zero-shot learning is one of them. I mean, there are many different applications of autoencoders. It's very, very powerful tool, right? Classification and regression, those are classical applications, but with the autoencoders, it opens quite a bit of new door. So, for example, I could really look at this as adversarial, input attacks, right? Can I really figure that out using an autoencoder? That's where the latent space comes very, very handy in those applications. Okay, so mathematical notations, nothing really new in here. This is exactly what we had before. X is dimension so we have n samples, each one of them with p dimensions. Basically means we have p features or p dimensions for the input. And then for each layer k, we have our weights w's, and the dimension of p to the k times p to the k minus 1, because it's really input from k minus 1 layer to the next layer k. And then what we are really interested in next is to visualize the weights. Let's really look at the weights, and what I will show you in the next few slides. We are really visualizing the weights without having any, without the bias, right? Just only the pure weights as they are. So what we will have is you have an MNIST data set, and this is the input, and then you have everything is fully connected layer. Again, the same network as before. So basically, if you look at the weights in here, These weights in here are really dimension of dimension 128 because the previous layer dimension 128, and the next layer is dimension here is 128 as well. So and so on. Sorry, the previous dimension is 784, and the next dimension is 128, right? And the same thing in here, the dimensions before is 128, the next one dimension is 64, and so on. If you look at the first layer, if you look at the fully connected autoencoder linear visualization, these are for only layer one, basically meaning that I'm just looking at these weights in here, right? This is the W1, right? Only these weights without the bias. So for the autoencoder, the linear case, we will have this one. But what we do is basically we really put them again. They are really concatenated. We just take each one of them and then just put them into an image, right? That's what we do basically in the visualization. And then we have these filters on the left-hand side. On the right-hand side, I have these nonlinear autoencoder filters in here, right? And you can see basically the differences between these. You can see this one a little bit. I don't know if I can zoom in, but maybe not. If you look at the differences in here, these are kind of a little bit more. I would say contrast is much higher than this one's in here. This one is a little bit more linearity in them. And if you go to layer, so this is you can see this components of the digits. You can really read the digits because we are layer one. You go to layer two, and then you start to look at some noise. And we have seen this before, right? You go to layer two, and you start to see basically some kind of almost like noisy. Layer three will be even noisier, and so on and so on. If you look at layer two in the linear case and layer three compared to the linear case, what do you observe the most? The difference between these two layers or these two layers? What do you observe? Exactly. So this one on the linear case is more sparse, right? This is more sparse, and that's a good thing, right? Because that will actually help in the optimization as well as it basically you are really dimensionality reduction is really working very well because you are really having only fewer features representing the whole data. That's what we really are after in this application. So this is a visualization is a very, very powerful tool to look at what's really happening in the autoencoder. If you use colored images, right, then what we'll see in the first layer is very, very interesting. You will have some filters that are really in charge. If you, for example, you have Cipher10 or ImageNet as your input data you're training on, what you will see some filters really capturing the color, right? So some filters really capturing the red, the green, the different color components, and some other filters having the edges. You will have basically vertical, horizontal, 45 degree, negative 45 degree, different whatever you have edges in the input. So the first layer is really as simple as capturing color and edge information in the first layer, and you see that basically very very clearly when you have a colored natural images. But in a digits case, it's much simpler in that case. So now, a very important visualization tool. What if I go and do this in here for visualization purposes? If I make this dimension 2, right? Not 32, I make it 2, just 2, right? In that case, I take my latent space. I can plot it on a two-dimensional space, right? So now imagine that I have my MNIST data set. I do the same autoencoder, fully connected, but now my latent space dimension is 2, right? And now I plot this on a two-dimensional space, right? And then I color code. So whatever I have in here, like for example, this purple here is for digit 0, right? What I have in here in the orange for digit 7. What I have, I don't know if this is purple, but this is another purple. Okay, this is the yellow one is digit 6, and the red one here is digit 8, and so on. So basically what you can see in here, even with this just very simple fully connected autoencoder, it really managed to have a separation between the different classes. That's extremely important. So it decorrelates them into this dimensional space, right? Although I'm using, which is really a huge reduction, you go from 784 dimension to a dimension of 2, right? This is a very drastic, basically, kind of reduction in dimensionality. Even with that, it really managed to have this kind of separation or decomposition of our digits into this two-dimensional space. And you can see now, it's for the most part, those are basically kind of, you know, if your sample is here, then whatever basically repetition space that you have is very powerful. But if your sample is somewhere in the middle, right? If your sample is somewhere here, right? If your sample happen to be projected here, right? That's a problem, right? Because that will be a combination between 2 digits, right? Or maybe 3 digits. Like if you are here, that will be even more problematic. It's like 5 digits, right? So it becomes non-realistic digit. And here's basically what we have. If you take this digit 5, and it really lies in here, the green here is 5, and it is a 2-digit 5. This is 7. But if you look at this, this is a combination between 5 and 7. See that? So now you start to think about the question that you had in the question number 4 in the exam, where you have this kind of adversarial attacks. This is basically an application where you can use this to detect such attacks, right? Because this is an unrealistic digit, right? This is this one here, right? It's a combination between 5 and 7. It just happened to be here. And then one of my former students, like years back, he was looking at this and modeled them, and he has quite a bit of very interesting theory about the adjacency piece. You can really play with the adjacency alone, and then you can really trick the model into figuring basically, you give it a 5 and it will tell you it's a 7, or vice versa, just with playing with the neighborhood in the autoencoder latent space. But that's for a different day. Okay, so overall, you can see it's working really very well, even with this huge reduction. There's another application where you look at document categorization, like, you know, like different text. You have, you know, all different kind of types of data, and basically it really did a very you know, very good job for the most part. It really laid out these, decomposed them into almost like a different space. Still, you have quite a bit of problems here. Like you see, some of these colors really are in the not in the wrong, but it should not really belong here. Same thing in here. This is very problematic area, right? If your input lies in here, that becomes a very tough spot. Okay, so all of this basically introduction to the autoencoder. Any question about autoencoders, visualization of autoencoders? Yes. No, or what? So the question is, how did I do this in here? So all what I did basically, you can look at this as different ways, right? So when the latent space itself is already done, right? I'm not doing anything with the latent space, right? I'm making up basically a digit, right? It's not a realistic digit. I input it, it will project it to this space, and you can see it's projecting between 5 and 7, which makes sense because that's how I created this digit, right? The other way around, you go to the latent space itself, right? And then you sample from it basically whatever you have in here. This is really, because it's a 2-dimensional, right? Literally, you have the coordinates for this point, right? You input this one, right? And now you run only the decoder side, right? Right? Basically, specifically, you have these 2 points because this is a 2-dimension, a dimension of 2, right? It's a coordinate. You input this one here, and you just run it here to reconstruct this image, right? And you get that digit. And that's what we did in here. Basically, in this example here, we just went here, we input basically a new digit because all those weights are already learned in the training. We're not really creating any new weights. This is an inference case, and then it gave us basically, because all what we did, we input the coordinates of this one here, and then it gave us basically back, which is amazingly between 5 and 7, right? Okay. Yes.
So are you suggesting that 5, 7, 8 have a variable, right? Because it's intentionally.
Yes, exactly. It's not a real digit. Yes.
Okay.
I made it up by just manipulating latent space.
It's how because it tells to.
So what we did basically, we just input the label, the coordinates into the latent space, and we run a decoder side, right? Which is basically just a combination of the weights, and we just get the image at the output. And basically, just a very validation that the image really is between 5 and 7.
So if you go to the next slide, does that mean that the
is confused between the two? Yes. No, these are the real data. These are real data. These are not basically the autoencoder It didn't really do a good separation as it did in the MNIST digit. But these are much more complex, right?
Yeah.
So these are really lying between them. So that's a problem, right? And
I
here.
guess my question is, how did you look at the first graph and know that the dot between the two clusters that they don't appear to be doing wrong?
Oh, because I did that intentionally. There's no data point here.
Oh,
This one is data point. This is data point. This one is no data point. I made this up.
got it. You didn't use this to detect that.
Oh no, I did not. I just input the 2-dimension here. I ran the decoder and they get me this image. Right? So this is not an input in the testing data. No, it's not. Yeah. Good question. Yeah.
When it's non-linear, it's not necessary that what corresponds to the distance in this case might correspond to the distance in the image space.
Yeah, you're talking about two things, but your second statement is extremely correct. Basically, the distance in the image space and distance in the feature space basically is not, a mapping between them is not that simple, right? It's not linear to say the least, right? But in here, all what we are really doing is we are inputting that latent space. The latent space is 2 dimension of 2, right? We're inputting basically that space, and then we are running the decoder only, and give especially this which is, it looks like between 5 and 7, right? We are biased. I mean, we have.
It's not necessary that something between the 5 and 7 cluster should look like something like.
No, it just happened here. Remember, this is the latent space. We're not really doing the linear, non-linearity is already done in the training, right? So now basically, in this 2-dimensional space, any point in here, it has to give you an image. That image is between 0 and 9, right? It can be any or a combination. This one is a made-up image. So the model never trained on this, right? In this space, there's nothing in here, right? So now if you run a decoder, it thinks is this digit, which is an unrealistic digit. It doesn't really exist in reality, right? It doesn't mean this here is the linear combination between 7 and 5. This could be a non-linear combination between 7 and 5, right? Because we cannot really tell what kind of combination is it, right? But we can see, or we can, have a hypothesis that it looks like a 5 in some aspect, but looks like a 7 in some other aspects, right? And then if you're interested in this, actually, we have a paper like from 7 years ago. If you keep moving it around, right? If you keep moving this around, you start to see basically what's really happening to that digit, right? But also adjacency.
That AutoEncoders kind of have like these sand images we kind of do that. So we kind of linearly interpolate between 5 and 7 and we do that. We kind of do that right here.
While training, we don't do it non-linearly. We do it linearly, not linearly, right? That's what we're doing, right? But what we could do after the fact, that after you have the representation space, now can you really operate on the representation space itself to do some other things? Improve robustness, right? Improve denoising application, adversarial attack detection, anomaly detection. That's basically what we are talking about. Then you can start operate on this one. But in the training, we're doing a linear activation function, right? I mean, that's how we get this to be a little bit more powerful than a linear case. Does that answer your question? Yeah. Okay. Yes. Okay, the question is, how can I use this for classification? So there is one missing piece in what you just said. Let me repeat it, but I want to correct it, right? So when you train, here is the mouse. When you train, what is your loss function? Loss function is the difference between the reconstruction and the input, right? So when you're training the whole thing, not only the encoder. You are coming up with the weights and the bias for every single neuron in the encoder as well as decoder. That's the whole process. You input, you run feed forward all the way, you reconstruct, you minimize the loss, you keep back propagate, and you keep doing that, right? You keep doing it. So as we did in CNN, the only difference in here, the output does the classification. We don't really have labels, right? We don't have labels. What we have is a reconstruction error. How good are we doing in the reconstruction error, right? That's what we're doing. After you finish training the whole thing, right? So you train the whole thing, you satisfy the conditions for the loss function. And now what you have a trained model, meaning that you have an encoder and you have a decoder, right? Now you go to the next step in what you just mentioned. You have now your image you want to classify, right? You input the image, right? In here. These weights are already pre-calculated in the training, right? You do this, and then now you have a latent space. So this latent space in here represents that input image. Now you take this space in here, and you run it into a classifier. You classify it, right? That's what you do, yes. So the only correction to your statement is that I'm not training only the encoder, I'm training the whole thing, because I'm doing the like reconstruction loss is very important, right? Now the question is, if you already have access to the labels, right? Is that a better strategy than training on the labels themselves from scratch? And the premise of the CNN and end-to-end is basically you have the input image, you have the labels, is an end-to-end, meaning what? The whole network will come up with its own basically understanding what the features should be and how to map the features into the space to the classes, right? What you're doing in here, if you fragment this into this, you say, I really want to come with the features. I want to come with the features. So this is one way to do the features. So I look at this. This is exactly what you're doing with Fourier transform, DCT transform. I mean, any of these Laplace transform. That's what you're doing exactly. Is a transform. Over there, we have a mathematically closed formula solution to give you those features. In here, you are using basically a training on data to do that for you, right? And now you use those features to classify, right? So now you have these two things. In most cases, in the general case, right? If you have access to the labels, then training an end-to-end will give you a better job, better performance in general, right? But not necessarily for every single application. When you go to digital, like computed images, like or any like radar signals, anything that has a computed basically component to it. The data is coming from a computation, not from natural phenomena, right? In that case, the general recommendation we have don't always apply, right? But for natural data like speech, like text, image, then if you have an end-to-end with the labels, it's better performance than having an encoder. But if you don't have labels, then this is the strategy. If you don't have labels, this is how you do it, right? This is how you do it. And actually, we look at in the transfer learning, we had a small, you really, when you have a pre-trained model, then you just freeze the whole convolutional layers, and you train only on the fully connected, the fine-tuning part, right? You could think of basically doing something like this, very similar. Like you're saying, I have unlabeled data, I run this through an autoencoder, I train, and now I have my latent space. And now I start to kind of, run this into, start to have intermediate step where I can label some of those images or some of those data. I can label them by hand, like 1 or 2 or 3 or 4. And then you have a weakly supervised one. So now a combination between the latent space, your hand labeled data, which is very, very small, like you spend like 1 hour to finish, I don't know, 10 samples or so. Then now you have quite a bit of things to work with, right? And that's basically we call it weakly supervised, self-supervised, and so on. Okay. Yes. We will not cover it in this class. Yes, but maybe I'm still looking at the last 2 lectures. That's why we don't have presentations. Maybe we'll just have 20. Was that? I have to throw GANs, generative network GANs, and the GANs will take some time. But I want to think of GANs as, you see this one, this generator. This is a generator. I mean, that's the shortest answer. But hopefully I will have time to go through transformer, GANs, and ChatGPT, maybe the last lecture. But I really want to cover explainability, active learning, sampling, and RNNs, sequence modeling. I think these are very, very important to cover. Okay. Okay, so now let's look at, so far we looked at fully connected layer. Now we look at convolutional layer. And it's the same transition that we had before. Why we go from a fully connected layer to a convolutional CNN or CNN? It's the same, basically, same motivation, right? We are sharing weights. We have much better, basically, preservation for spatial locality. If the data really have spatial information like images, for example, and so on. So there is that kind of, if you list these for anything from MLP to CNN, it's the same thing from fully connected autoencoder to convolutional autoencoder. Nothing really different in this case. So now we looked at basically a much more familiar setup in the literature, which is the autoencoder looks something like this, where in the encoder is really very wide on the left, but it's really very narrow on the right, and then the decoder is the other way around, narrow on the left and then wide on the right side. But the same process. The encoder is the same function as before. The decoder is the same function. The only difference, now I have a convolution. But remember, in the encoder, we have a convolution followed by a pooling, right? But now in the decoder, what do we have? We need to reverse this operation, right? So we have to do an increase in the dimensionality. So we have to do pooling and convolution, meaning that we refer to this as transposed convolution, right? With the slide. Let's look at this in more detail. So imagine that you have an input of 2 by 2. So the sample is 1, 2, 3, and 4. And then you want to output this, basically in the decoder side is 4 by 4, right? So now you have to have some kind of criteria, right? So if your criteria is the nearest neighbor, then basically you look at this, you repeat the 1. So 1 will repeat 4 times here, the 2 repeat 4 times here, same thing for 3 and 4, right? So that's your nearest neighbor. If the criteria is bed of nails, right, then you will have 1 here and everything else is 0 here, 2, everything else is 0. But you have to have an agreement throughout your setup that the position where your sample will be preserved is the upper left corner, right? This has to be there. So you could replace that with max pooling. So for example, on the encoder side, if this is the input to the max pooling function, then if it's the output is a 2 by 2, then this is what you have in here. The max is 5, the max in here is 6, the max in here is 7, the max in here is 8. This will be the output. If you do the inverse of this operation in a decoder, you start with this 5, 6, 7, and 8. And now if you are using basically this bit of nails or the max, I'm pooling with bit of nails, then the 5 will show up here and here and here, as far as you agree that basically where the locations are. And this is basically something you don't only encode the digits, but also the indices, right? You have to know basically what the indices are in this case. And if you look at this as 1, 2, 3, or 0, 1, 2, 3, 4, 5 is location 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? That's what you're already encoding in this case in here, 5, 2, 12, and 15. Yes.
Maximum point is the only count that.
Yeah, usually what you do in here, you do the same thing in the decoder. Yeah, Rahman. The indices. So you encode basically, you have the values here, but also you concatenate the indices. So basically means 5 will be at location 5 in the output, right? And this one here, 6 will be, which is this location here, will be at location 2, and so on, right? The indices. And I saw this many times. Students do this mistake where the indices actually carry quite a bit of information, right? Even if you just say I want to make everything in here equal to 2 or 5, that will give you quite a bit of information in the reconstruction. Actually, you will have quite a bit of you will see a digit, especially if it's MNIST data set. You will see a real digit. I mean, it's a correct one. Actually, it's very blurry, but it's correct digit, right? So you want to be careful basically what you do. But yes, you use indices in this case, right? If you use max pooling in here. But just be careful and whenever you have what the code is doing, as you have to be careful there on what is really passing through the latent space, right? Yes, sir. Yeah, I mean, it depends on the application, depends on how fast you want to do things. But yeah, I mean, it is not really because remember at the end of the day, these are all intermediate, right? And we're trying to figure out the way. So it will affect the optimization and the convergence speed, right? More or less, right? Will it have a yes? I mean, it depends on the data itself. Actually, at the end of the day, yeah. I don't think we have it in the literature a solid conclusion which one is best for when. But I think it's speed for the convergence in the training is really the criteria. So that's the bottleneck usually. Yes. Where is that? Oh, thank you. Yes, this is a, yeah, this should be a 0. Thank you. Thank you, Joshua. Yes. Yes. Yeah, you could, yes. But remember, if you are doing pooling, you lose that information, right? You lose basically what are the values of the other ones. What you want to preserve was the location of that digit, right? Or that number in the pooling one. But in here, we're not really interested in the values 1, 2, and 3. We're not interested in 2 and 1 or 3 and 4 here. We're interested only the location of where these should be when we do the unpooling. Right? That's where the indices come. I don't think there will be as far as you agree where that value should be, because you are replacing this whole thing now with the value of the average, right? Now you could just say, as I mentioned here, you could just decide, where is it? Yeah, here. I just said the upper left corner. That's it. That's I don't have to pass any indices or anything. So the upper left corner is with the location. I could do the same thing in here, right? I could just say the upper left corner is here, but you could really also preserve the indices as well. Okay. So different implementation will have different coding. So just watch out what's happening. Yes, Samir. You just pick. I mean, both of them are max, right? Yeah, just one of them. Yeah. Yes. That in the representation space, right? That's basically either in the weights or in the Z itself, right? In here, we are just looking at the intermediate ones, right? This is in between, right? And here. So do you want them to be closer to each other or not? That's a good question. I don't think of any reason why you want them to be closer or far away from each other. Yeah, I cannot think of a criteria when they should be closer or should be far from each other. I don't think it will matter much. I cannot think of a reason why it will matter. Yeah, good question. But if you have a 2 by 2 pooling, then those will be in the 2 different regions. Yeah. Uh-huh. And the 5 here. Yeah. But I would choose one of them. Yes, one of them. Yes. But his question is interesting because say if you choose this 5, let's say this is a 5, you choose this one, then this will be closer to this one. Will that make a difference or not? That's what his question is basically if the 5 is close to the 6 in here, or this 5, will that make a difference or not? And I don't think I cannot think of a reason which one is better. I cannot think of a reason. I don't think it's the data. I think it's I don't think it really matters. I don't think it matters.
So like you want the reads in the encoder, like let's say the LP of encoder to correspond perfectly or like very closely to the LP of the decoder. In that case, it makes sense when we kind of have a similar problem, kind of.
Yeah, but the question is, if I have a 5 here, right? So now do I pick in the max pooling, do I pick the 5 here or there? Right? And will it make a difference or not? And I cannot think of a reason when it will make a difference. I cannot think of a reason. Yes, sir? The variation autoencoder. Yeah, the variation autoencoder. Yeah. Yes. Encoder, decoder, not encoder. Yeah. Yes. Yes. Yeah. Because we are doing the construction. Yes. Yes. I mean, when you go to the GANs, then there will be a difference. But for the sake of this discussion, yes, they are a mirror. But we have this class. You can do, if you are working with the multimodal data, right, and you have a zero-shot kind of learning setup, then there will be some variation. You can do some variation. It's not easy to train, but you can do variation. But for the sake of this course, it's all mirror. Is a mirror. Yeah. Okay. So this is basically kind of just how the operation looks like. Let me see if I have. Yeah, let me go through this one. Okay, so you have this one here, and then you unpool. Basically, you populate, and then we have stride of 2, right? So you have stride of 2. Just keep an eye because we'll have stride of 1 next. Stride of 2, you populate in here, and you shift by 2. You populate, shift by 2, populate, shift by 2, because we have stride of 2 in this case. If I have stride of 1, right? If I have stride of 1, so this is the input, this is my kernel, right? This is my filter. So now, if I'm operating on the 0 only as the input, right? Then 0 times 0 will give me a 0. 0 times the 1 will give me a 0. 0 times the 2 give me a 0. 0 times the 3 will give me a 0, right? If I'm operating on the 1, right? Then 1 times this kernel will give me this one, right? If I'm operating on the input 2, 2 times this kernel will give me these values. If I'm operating on the 3 as an input, then 3 times this kernel will give me this kernels in here. And now I'm having basically stride of 1. That means basically there will be some overlap. What do? You add them all together, right? So basically this will be the output from here. We didn't really have that problem when we have stride of 2 in here. We didn't really have any overlap, right? So that's the difference between this same dimension for the kernel, same dimension for the input. The only difference is the stride dimension. This is 2, no overlap, no problem. This one here, we have stride of 1. Basically, it means there's an overlap I have to add. So the stride of 1 give me the output to be dimension 3 by 3 in this case. Does this make sense? Overlap, you add. This is all in the decoder. It depends on your setup, right? This is just an illustration here. When you have an overlap, you just add them together. And I think I have a generalization here. Generally, this is what you do. Now, we're adding a pad of 1. Right? So now we are adding basically padding with just dimension 1 all around, right? I want to go back to the same equation that we have in the scene. And remember that equation about the filter, the input size, filter size, stride padding divided by the 2 times the filter size. Is exactly the same setup that we have, or 2 times the padding. So if you have a pad of 0 in here, pad of 1, then I will have this output in here. And you will have, even if you have stride of 2, you still have an overlap because of the pad of 1, right? So you add basically in here, and the same thing in here. You keep adding them all these together. And that's basically the general case, right? This is exactly what we had before, right? Remember this? The convolution layer from previous, from the CNN side. So you could really have different stride, different pad, different input, different kernel sizes. Okay. So whenever you overlap, you add in the decoder side. Okay. So now we do the same input data, but now we change our fully connected layers to be 2 convolution layers. So we have 16 filters in the first convolution layer, and then we have a max pool. We have a second 8 filters in the convolution layer number 2, and we have the latent space basically in here, which to produce them after the max pool. And then we do the same thing operation in the decoder, and basically we reproduce or reconstruct our images. So now we put this. We had this before on the left-hand side. We had this in the middle before, and now we have the convolution autoencoder on the right-hand side. Of course, if you look at the mean square error is lower, like there is almost another 60%, 70% reduction. But if you look in here, basically these will look sharper, right? If you look at, all of them basically they are. I don't know if it looks, but I think even the screen here looks good. So this is a little bit sharper than this one, and this one sharper than this one, right? So the convolution actually gave you that. What this means is that the latent space that we learned here is a much better representation of the input data compared to what we had learned from this network or from this network. Okay, that makes sense. Okay, now we go to regularized autoencoders. So what we learned so far, we really learned some useful representation. But now, what if we can not limit ourselves to lower dimension, meaning capital K is less than P. What if we look at higher dimension in here? We like to increase the representation space to be higher than the input data, right? And that's very, very useful when we are really trying to learn a very, very complex data distribution. So our job is not to compress, but our application to really understand the representation space. But that's the case if this is a very large dimension, then we need to impose some kind of constraints. And that constraints is we'd like to make it sparse, right? And here is basically the case between a z dimension of 10 and a z dimension of 2. Even with this, even both of them are really compressed compared to the 784 dimension of the input data. You see basically the larger one is capturing more features in the input data compared to the lower one. So you can really extrapolate that thought and say I can really make P larger, K larger than P, but as far as I impose some sparsity on it, then I will learn much more complex structure in my input data. And that's basically very, very, very common in this application. I just came to mind, I think there's an application I want to go through it. Maybe next time I'll go through some application next time, but when that can be very, very helpful. Okay. So what we want to do is we want to avoid what we refer to as identity mapping, right? Basically, if you really have kind of a very large representation space, then there is a case when you don't really have enough capacity in your model, where basically the model in the training will just copy the data from left to right, right? That's basically where you're not really learning much about the space in here. So let's get to it. So what we are really looking at is more of a sparse representation to really exactly do this. And I showed you an example a long time ago about the face recognition, where basically you have different filters, one for the parts of the nose, the eyes, the eyebrows, the mouth, the ears, and basically each of these are components. If you look in here, we can really have that sparse representation. It will learn components, and I mentioned earlier about the chair application. And here you can really see the 7, basically, this part of the 7, this one part of the 7 here, this part of this component. But each one of them could be part of another digit. This could be part of the 9, this could be part of the 9, this could be part of, I don't know, 2, for example, this could be part of a 3, right? So this is where sharing of these filters among different input data representations, but it's sparse where we can really decompose our 7 into these different 5 filters in here. And that's what we are really trying to do when we increase that size of dimension of the representation space. However, we have to add the regularization. Again, our loss function, again, is same as what we have in the exam 2. That's where you can impose what you are really trying to do. So the first term in here is, again, is not changing. We are limiting, or we are trying to minimize the reconstruction error, the difference between x and x hat, and the mean square error sense. But also we are really adding constraints. That's basically a sparsity constraints in here. And this is there's a lambda which is really control, as we did in the lasso and ridge regression, for example. We had a parameter to tell us how much we're gonna regularize our training, right? So now there are 2 ways how you can impose sparsity on the z. Remember, this operation gamma here is operating the z, right? So you want to make the z as sparse. So either you do the L1 or the KL divergence in here. So in the L1 is really simple. Basically, you look at the L1 norm, this is the sum over the jth latent neuron over all the zij's. That's basically I for input xi. And you're really trying to make basically this equal to, or minimize this, basically meaning that you want to make this as 0 as possible. Again, remember from the regression side, that means if I have a zij that's really very, very small, I want to make it a 0. If I'm minimizing this, if this is very, very, very small, I want to make it basically equal to a 0. So I'm zeroing out the small component or the small coefficients in this case. Okay. Now in the KL divergence, let's look at this as kind of a background about the KL divergence. Okay. So let's really look at or create this row, right? Row hat. So now most of these latent neuron activations, they are really very close to 0. So that's basically in the L1 norm, we try to make them all 0. In this case in here, let's look at this row, which is basically the average among all this activation for this specific neuron, Zij. This I is the Xi, the input sample, and J basically is the J latent neuron, right? And then we are really averaging for all samples in, right? For that specific neuron Zij, right? So all those activations for that specific neuron, for all input samples in of them, I'm really creating this average, which is the rho sub J, right? Which is rho hat in this case. So now we want to constrain in the KL divergence, we want to constrain basically this rho hat to be close to zero. We don't want to make it a zero. We don't want to make the Zij's to a zero. We want to constrain them to be close to a zero. We don't really want them to, fire up and be very large, right? So how do we do that? We can really look at this as if we look at each one of those activations as an observation of a Bernoulli random variable, basically meaning that is just a Bernoulli distribution, like P and 1 minus P, right? Or K and minus K, whatever the probability is, right? So now, then what we're really doing in here, this rho hat is nothing but basically the observed expectation of that process, right? But now we have kind of an ideal case, which is rho, which is coming from the Bernoulli distribution, right? So now, if the KL divergence is looking at the distance between the rho and the rho hat, basically what our data is, right? Rho hat, and what's really the ideal case, which is the rho in this case. And that's basically where we are trying to minimize the dimensionality of these Zij to make them smaller, close to a zero in here. So all what the KL divergence, right, to kind of measure the distance between them, we're really trying to minimize the distance. We're really trying to make them as close to zero as possible in that case. So if you put the KL divergence in the general case, if you see it in the literature, between two distribution, capital P and capital Q, they're nothing but really summation over all x, the P of x log of the ratio between P and Q, right? That's basically what we have. But what we have right now, we have the rho and we have the rho hat, right? We have the difference between the Bernoulli distribution and the rho hat. So we have the rho log of rho to the rho hat plus 1 minus rho, because this is Bernoulli distribution, log of 1 minus rho to the 1 minus rho hat, right? And basically that's where the rho hat is what we have from our distribution here. If that value, really summing this over all the j's, right? So if that value is equal to a zero, that means we have the two distributions in here are really equal to each other, right? And if they are not equal to zero, that means there's a difference between them. So if you look at the right-hand side, this is if I'm looking at the x-axis, our rho hat, and the y-axis, our KL divergence. How far? So if you look in here, as far as my rho and rho hat is really very close to each other, then basically I have a very close to a zero. The divergence is very close to a zero. As rho hat increases, right, then the distance becomes really very, very large between them, right? So now what you think of, then I have this kind of a control parameter, a knob to control my sparsity, right? In the L1 here, remember this one here, I have no control. I don't really have any knob. Once I have this function, it just happens, everything will be a zero if they are very close to a zero. In here, I have a control. How much I want this to be the distance wise. So I can, this rho in here becomes my hyperparameter, this rho in here, right? This rho. So this whole curve, right, is for 0.05. So the rho is 0.05. That's why at 0.05, distance is smallest, right? That's what I'm doing. I'm trying to really make the distance as small as possible. But as the rho hat increases, distance becomes much larger, which means what? As I'm optimizing, as far as my rho hat basically is really much higher than the rho in here, then I'm still not converging, right? I'm really trying to reduce that as much as possible in this case. So the difference between the KL divergence and the L1 norm is that the KL divergence give me this rho as a control parameter, a hyperparameter to control my operation. This curve will be a little bit different if I have rho equal to 0.1, for example. But usually we have rho is very, very small in the general case. I really want to stop here to make sure that you understand what this is. Understand that? Don't lose the big picture. We are trying to do what? This dimension is large, not compression anymore. We now wanna make this representative space not to have a, if we keep it like that, then most likely we'll have identity mapping, right? Right? Because this dimension is much larger than this. Then you just basically the easiest for the encoder, just basically kind of copy things, right? So you have identity mapping, you're not learning much, you're memorizing, right? There's nothing happening. Now we want to add a constraint, which is basically make it sparse. Now we have two mechanisms: L1 regularization, which basically means any z that's very small, very close to a zero, I make it a zero, right? I have no control over that, right? It's just with the learning process, everything will be this one will be a zero. In the KL divergence, I will input this row, right? And the row is basically is just a, again, in the KL divergence, I have a distance between the two distribution, the P and the Q. Now I have a hypothesis or assumption that I'm drawing this from a Bernoulli distribution. So basically I have the row to the row hat. What is the row hat? It's basically the average of all my activations for that specific neurons, right? And here for all in samples for the specific neuron, right? And now I have my row, which is the input, as in this case 0.05. If it's very close to it, it's very close to a zero. It's much higher row hat than row, then you can see distance becomes really much higher. And there's just a comparison between the two I just mentioned. So let's look at some, I think, yeah, here. So this is the left-hand side is a fully connected linear autoencoder. This is the sparse with KL divergence. When I have lambda is this regularization term. Oh, one more. This lambda, right? This lambda, right? Not rho, is lambda, right? So this is 0.001. In both of these cases, rho is 0.05. In here, I have KL divergence, but I have lambda is equal to 0.03, right? So we have seen this before, the one on the left-hand side. But you can see the two on the right-hand side in here, they are what? They are much sparser than this one. They are really sparser than this one here. But if you look at the difference between these two in here, remember, the lambda is higher here. Basically, that means what? We are adding more weight to the regularization, to the sparsity, right? So you will see this one is a little bit sparser than this one. You can see even from this row here, right? You have only this one here is even within each one of them. I wish I can. If you look at this one here and this one here, we'll have even within the same filter is really sparser than this filter, right? With the same filter as well, right? With the same one. So it's really much more compact representation in here. And if I do that again for L1, right? Remember, the difference between you compare. Well, I want to look at the two on the right-hand side and compare them to the previous one. Look the difference. So which one is more sparse? This one, the L1. Because why the L1? It makes things that are very close to zero, make them zero, right? And you can see that in here, right? You can see that in here. These are the W1, yeah, layer one. This is W1, layer one, at the encoder stage. You see this sparser, right? There's a difference between these filters. Okay, I have 1 minute left. I can squeeze this here. Okay, denoising. This is all what we need to know. If I have clean data X, right? And now, and this is very important. I really literally we need only 20 seconds. I have my data X. I can add noise to it, Gaussian noise, whatever noise you can think of. I create X tilde, which is noisy, right? And I do this autoencoder. My reconstruction, I compare X hat with what? With X, not with the X tilde, right? So I'm trying to reconstruct the original data from the noisy data. You see that? That's what I'm doing. That's why we call them denoising autoencoders. Okay, and that's basically what you will learn from here is nothing but a denoising algorithm, a denoising representation, right? So now what we are trying to do is why we are inputting what when we add the noise and we are doing this whole training, then if this is your data and the black basically curve in here, if this is your original input, as if you are really trying to create a vicinity around it, any data that's corrupted and it lies within that region, it will be mapped to this original data. That's exactly the concept of denoising autoencoders. So if this is the 9, then it will map basically to the correct 9. Either it's very noisy or it's very blurry. It's basically both of them will map to the 9 in this case. And that's all what we have in the denoising. And here's basically some kind of algorithms. I have a fully connected linear denoising. This is the input. Same thing in here, but now I have nonlinear, and you can see the nonlinear one is much better, right? This one is much better. Look at the 5, for example. Look at the 2, it's much better. When you go to Cypher10 and ImageNet, it will be even much more impressive results. Okay, so by that we finish autoencoders. All right, we'll see you Monday. Thank you. I have the exam papers for those who haven't picked the exam papers.
Monday too.
Yeah.
Weekly, right?
Okay.